All right. Well, this is the last day. Well, last lecture for differential calculus. And this is the last topic that we'll cover. And this is kind of meant to be a precursor and predecessor and kind of get you in the idea of if you're going on to Calc 2, where are you going to start now? I will go ahead and say, if you come back to this video later, you're going to go, we didn't start with indefinite integrals, we started with Riemann sums. I know that, but once you get out of Riemann sums, you get into indefinite integrals. And it's kind of like in Riemann sums are to Calc 2 what limits are to Calc 1. They lay the groundwork and they lay the foundation. So this is kind of how are Calc 1 and Calc 2 related. And if you go into Calc 3, get ready for just a hodgepodge of a bunch of other stuff in higher dimensions. But indefinite integrals. So a corollary that we get from the mean value theorem is that functions with the same derivative differ by only a constant. So think about why that would work. So if I gave you just 2x is equal to 2x, that's very clear. But you know that x squared plus 3 does not equal x squared minus 4. So if this is f of x and this is g of x, which aren't equal, but their derivatives are equal, then the only thing that separated them was a constant. Because remember, a constant is just going to be on a function. It's just going to add a vertical shift. So one thing to take into account is I can use that to my advantage and kind of now I can start to get this idea of, all right, I've taken the derivative, and this is kind of to get you in the mindset of, I refer to Calc 2 as you have to start thinking backwards. And this is where we'll introduce that. Because Calc 1 is, I need to take the derivative of this function. Calc 2 leads you into the mindset of, what did I take the derivative of to get this function? So for this example, we have v is equal to cosine of t minus t sine of t, and s of 0 is 1. So I know the particle's position when the time is equal to 1, or when the time is equal to 0, and I know its velocity throughout. And if you remember our chart, we had position, velocity, acceleration, and then you also have jerk. And we said if you took the derivative, you move down the chart. Well, what if I want to go up the chart? Is that possible? And the answer to that question is yes. So what I'm going to do is I'm going to look at this function first. So cosine of t minus t sine of t. And if I look at it and I kind of think for a minute, I can see that, okay, this is v. I can think about this as 1 times cosine of t minus t times sine of t. But instead, I'm going to make this plus a negative sine of t. And this looks like product rule, with t being my first function because the derivative of t with respect to t is 1, and then cosine being my second function because derivative of cosine would be negative sine. So I can kind of come to the conclusion that, okay, my position function, s of t, is going to be t times the cosine of t. But remember, they differ by a constant, so I'm just going to go ahead and add this plus capital C. When you get to Calc 2, or if you get to Calc 2, plus C is going to be the cost of a lot of easily obtained points. So make a good habit now of not forgetting to add C. So how do I address that constant? The way that I'm going to address it is I have this initial information. I know that at 0, the function is 1. So s of 0 is going to be equal to 0 times cosine of 0 plus c, which is equal to 1. So I can conclude that c is equal to 1. And thus, I now have that the position function is t times cosine of t plus 1. And so I was able to get the position based purely off of the velocity and 1 point, just one. I didn't need multiple points. All I needed was a snapshot of this function at 1 point. And we'll talk about it on the last slide, or the second to last slide before the homework, as why is it important to have those multiple values, or why do you need those initial values, which we will refer to as initial conditions. So typically what we say is if I take the derivative of a function and I get the lowercase function, then we say that capital F of x is the antiderivative of lowercase f of x. Just kind of makes it easier to think about. Because if you think about it, you're going backwards. So typically when you think about derivatives, like with power rules, you reduce it. So going from capital to lowercase is just kind of one of those little, I don't know if it's a cultural thing or maybe it is across the world, but at least in the US, this is the kind of standard idea that some people take when just trying to write it down at first. And the nice thing is you can the reason I said that plus c is so important is you create this family of functions that is the set of all the antiderivatives of f of x. So in that case, if I take the derivative of, or the antiderivative of one function, I can tell you every single one of its possible antiderivatives by just throwing a constant at the end. And then if I have that initial condition, then I can actually tell you the specific one that you're after. So in a lot of these right now, if you do go to Calc 2, you will find there are rules and specifics that will aid you in finding the antiderivatives. But here, what you're going to discover is all of these functions right now are just going to be kind of based off of a little bit of sight and familiarity, not necessarily a specific antiderivative rule. Again, Calc 2 does have antiderivative rules, but we're not working with those right now. We're purely looking at kind of an intuitive standpoint. Intuitive, that's the same thing. Way of thinking about it. So like just starting with 4x cubed, what do I take the derivative of to get 4x cubed? Well, it's x to a power. So I know that it had to decrease by 1. So I'm going to say that this would have to be x to the 4th. And then I'm going to remove the 4 and just leave it as a 1 out front, because I know that here, if I take the derivative of x to the 4th, that would be 4x cubed. All right, that lines up with this one. Good. What about now minus x? I'm going to use the fact that derivatives are linear, and I'm just really going to worry about what's the antiderivative of x. Well, this is x to the 1st. So it would have to have been x squared beforehand, right? But now there's an issue. If I take the derivative of x squared, now I get to 2x, which is not what I have here. But what if I threw a 1/2 out front? If I threw that 1/2 out front, okay, now I'm in business, because this is going to be 1/2 times 2x if I take the derivative, and the 1/2 and the 2 cancel each other out. And again, this is what are all the antiderivatives. So plus c at the end. I have seen before people have a stamp of plus c just so they don't forget it. It's one of those things that is very, very crucial for antiderivatives and the idea of all antiderivatives. Now, what about this one? 2x squared. All right, well, like we talked about before, this is going to have to be x cubed, because it became x squared. But that means if I do that, that's going to bring down a 3. And I don't have this 2 left over. So I need a 2 out front. But I also need to cancel out this 3, so I'm going to put a 3 in the denominator, so I'll get 2/3. And then you can check. Bring down the 3. You get 2/3 times 3x squared, which would become 2x squared. All right, so we're good there. Now I'm going to do plus. All right, what would I take the derivative of to get sine? Well, if I take the derivative of cosine, I get sine. All right, that's a good start. But the thing is, I get negative sine. So if I do plus cosine of x, that doesn't really work out. But if I do minus cosine of x, that would work, because derivative of cosine of x is negative sine. So derivative of negative cosine of x is negative sine of x, which would be the positive sine of x that I'm after. And then that takes care of all the terms. So then we just get plus c at the end. So then f of x is equal to 2/3 x cubed minus cosine of x plus c. All right. This one doesn't look like a product rule. But notice here, and again, we're going off of intuition. I'm leaving aside all Calc 2 knowledge I've had up to this point. I'm treating it as if I don't know Calc 2. And I'm just trying to go off of this intuition. So there's 2x, and there's x squared. Here's u, and here's u prime, if you want to think about it like that. So this looks like a chain rule, because here's the derivative of this inside function here. So the problem is, though, all right, so I know it's something of x squared. Is it just cosine of x squared? Well, remember the way chain rule works. Derivative of the inside, and then derivative of the outside. So this would be 2x, and this would be negative sine of x squared. So it doesn't work for cosine, because when you do chain rule, you have to take the derivative of both things. So, but I do know that if I take the derivative of sine, I get cosine. So this needs to be sine of x squared plus c, which does work out, because if I do the derivative of a constant, dies goes to 0. Derivative of the inside function is 2x. Derivative of sine, because remember, you would think about it as it would be u equals x squared. So really what we would be doing is sine of u, and then it would be the derivative with respect to x would be of sine of u is the derivative with respect to u of sine of u times the derivative of u with respect to x, to which u is equal to x squared, which then gets you back to here. So we've done multiple examples. We've done the reverse of a power rule. We've done the reverse of a trig function. We've done the antiderivative of a chain rule, and the first one was an antiderivative of a product rule. So antiderivatives are undoing the derivation process and asking you, what did you take the derivative of to get this function? And right now, that's the intuition you want to go with, is what did I start with if I ended up here? So at first glance, this looks like the sound hole of a violin. What it is a, I know it sounds like I'm making this up, it's intended to be an S, because like I mentioned before, the Riemann sum is to Calc 2 what the limit is to Calc 1. So Riemann sums give you integrals, and so instead of having a sigma, which you do use when you do Riemann sums, you have this kind of, again, it's a sound hole off of like a violin or a cello, something like that. But it's just the fancy S that signifies antiderivatives. And the same way we did derivatives with respect to a variable, you do antiderivatives with respect to a variable. And you read this as the integral. That's what the fancy looking S or the sound hole is referred to as. This is the integral sign. It's the integral of f of x, or just the integral of f with respect to x. So that dx from the derivatives returns, but now instead of the denominator, it's up here beside the f of x, dx. Kind of like if you thought about the linearization when we did the estimation, we had dy equals f prime of x dx. Now it's just f of x dx. And what this is it generates the set of all antiderivatives of f of x. So kind of going back to, if you solve this in a weird way, I say in a weird way, that's differential equations, which is another class. That's after Calc 2. might be after Calc 3 and linear algebra, depending on where you are. Then the antiderivative of f with respect to x is equal to capital F of x plus c. So if I'm saying what is the integral of x cubed plus 4, I'm saying what is the antiderivative of x cubed plus 4. And again, still think about it the same way, just kind of reason your way through it. All right, here's x cubed. I know that beforehand this would have to be x to the 4th. But if I bring down the 4, I don't get 4x cubed. So just stick a 1/4 out front to counteract it. All right, then this plus 4. All right, you're just left with a constant. So what do I know that when I take the derivative of it, I'm just left with a constant? If I do the derivative of x with respect to x, I get 1. All right, so that works. So, but I want a 4, so I'm just going to throw the 4 in front of it there. Again, very informal reasoning your way through it. And then again, plus a constant at the very end. Antiderivative of cosine of x. And one thing I didn't state here, and this is nice, notice when I did the antiderivative of the sum, I just said, okay, what's the antiderivative of this plus the antiderivative of this? Like derivatives were a linear operation, integrals themselves are also linear. Now, one thing this doesn't mean, remember linear is split over a sum. The antiderivative of two functions multiplied together is not just the product of the antiderivatives. So please don't do that. That was why the previous function we had to do the chain rule, or the anti-chain rule. And then cosine of x, a little bit simpler. I know that if I take the derivative of sine of x, I'll be left with cosine of x. And then I just have to add a constant to it. So how do you know you're correct? So here's tangent secant squared, which would be, if you did chain rule, that's the same as 1/2 secant of x times tangent, because if I do this derivative with respect to x of 1/2 secant squared x plus c1, I'm going to get 1/2 times 2 secant of x. And then the derivative of secant is secant x tangent x. And then the constant dies. And that would leave you with the tangent of tangent x secant squared x. But at the same time, tangent secant squared is also just 1/2 of tangent squared x squared, or tangent squared x, because you do that derivative, tangent squared x plus c2, that's going to be equal to 1/2 times 2 tangent of x, and then derivative of tangent is secant squared. So which one's correct? Key thing is you remember the constant. And if you differentiate the answer, you get the integrand. So in this case, I already went through this. If you differentiate them, and these need a 1/2 out here, you still get the same thing. The difference is going to just depend on what the constant is. They're both right. The difference is just one person may see it as getting 1/2 secant squared. The other person may see it as getting 1/2 tangent squared. The nice thing is, though, they both come out the same, and it's all going to depend on your constant. Because if at, let's say, pi over 4, the original function was 10, then pi over 4 is going to be different for tangent and secant. But what that also means is the constant is going to be different for both of them. So that constant is going to be your kind of safety net. And it's going to say, okay, these are both okay. They're both perfectly fine. Are they the same? No. And that's okay, because your constant is going to counteract and help out and affect what you need. So make sure that if you have a situation like this, and this is one of the very few and specific examples I like to show, just to say it's okay not to have it look exactly the same. Think about like trig identities. Trig identities are not always, they're the same thing, but just look a little bit different. So same thing. Here, your antiderivative of the same function can be different, but that constant is what's going to help counteract it. Or not counteract it, but help keep it in line for what you need. And that's kind of how they're both correct. Now, one application is the idea of initial value problems. So, like beforehand, we knew the velocity. Now I want to know, I'm going to start even further down. I want to know, I've got the acceleration. How do I get back to position? So you have y double prime is equal to 2 minus 6x. Y prime of 0 is 4, and y of 0 is 1. So what you can think about this is the acceleration, or sorry, this is the velocity. And this is your position. And you're starting with your acceleration. Now, notice I've got the specific values for y and y prime. And you may go, okay, well, do I need those? The problem is, without them, you get a bunch of constants that don't give the specifics of the equation. You need these snapshots of the equation at certain points. I'll do it with the constants and then, or with the initial values, and then without the initial values. So, all right, if I've got y double prime is equal to 2 minus 6x, that means y prime is going to be, all right, so this is 2, and again, just think it through, same idea. All right, this is going to be 2x, because if I do the derivative of x, that leaves a constant of 1, so I'm just going to throw the 2 out front. And then this would have had to have been x squared, which means I need to leave a 3 out here. So that gives me 2x minus 3x squared plus c. And then I know y prime of 0 is 4, which means 2 times 0 minus 3 times 0 squared plus c will give me that c is equal to 4. And life's good. If this had been, say, y prime of 0 was 1, you would have just done 2 times 1 minus 3 times 1 squared, and then just solved for c. And you still would have got, and it would work out and give you the constant that you're after. So I've got y prime is equal to 2x minus 3x squared plus 4. All right, then if I have y prime, what about y double prime? Or sorry, I've got y prime, so now I just need y. That's going to give me, all right, Now we're going backwards from the y prime equation. So if I've got x here, that means I had to have x squared before it. And don't need the 2 out there, so good to go. Minus, all right, this would have to be x cubed. All right, and that 3's don't have to worry about it. Plus, using the same logic with the 2, this is just going to need to be 4x, and this will be plus c. Like before, I knew at y of 0, I get 1, which is going to leave me 0 minus 0 plus 0 equals c. So that gives me that c is equal to 1. So my final answer is y equals x squared minus x cubed plus 4x plus 1. And that solves the initial value problem. Now, I said specifically that having those initial conditions is necessary to discerning the final equation. I'll show you what happens if you don't have them. So we'll still have y double prime equals 2 minus 6x. Y prime is going to give you, we already said this one, it's going to give you 2x minus 3x squared. And I'm going to say this is plus c1 because we don't have any values for the constants yet. So now if I integrate this one more time, I'll get y equals x squared minus x cubed plus c1 times x, because this is just a constant. This is like a 2, 7, pi, 33, whichever. It's just another constant. And then plus a second constant to throw that in. And if you notice here, notice it looks basically the same thing, or as the same that we had here. X squared minus x cubed plus 4x plus 1. But now we have x squared minus x cubed plus c1x plus c2. Those initial values give you exactness of the equation. We've found the general solution of any function that has the second derivative of 2 minus 6x. Kind of like the antiderivative was the family of all of the functions, or the functions with a derivative whatever. This is that capital F of x plus c. But now what you can think about is you're integrating capital F of x plus c with respect to x. So that's giving you whatever the antiderivative of this is plus this constant times x plus a brand new constant. So you're creating another family of functions. You're saying this is the set of functions that all have a second derivative of 2 minus 6x. So the initial value problem without having those, initial values just gives you another family of solutions. But typically, like, you think about like a rocket or something that has like a parabolic arch. If you know like initial velocity and acceleration and its height at a particular point, you can then use those snapshots to get the full picture and follow its exact trajectory. And that's what we were doing here with initial value problems. And so with that, this is the end of the differential calculus course. If you're not going to take Calc 2, then I hope this was a good class. If you are going on to Calc 2, I wish you the best of luck, and good luck in all future endeavors.